So good afternoon, everyone. Welcome to this, sorry, now it's September, September edition of the NITheCS Mini-school. My name is Francesco Petruccione, and I'm the director of NITheCS. And today we have the great pleasure of having Sayantan Ghosh with us. Sayantan is completing his PhD in the Department of Mathematics of BITS Piladi in Hyderabad in India. And previously he earned his master's at the Indian Institute of Science in Bangalore. Yeah, and he kindly agreed to give us a mini school on this very interesting physics of wormholes. And he promised that the mini school will be accessible to non-specialists in the field. So provided we all have a basic knowledge of quantum mechanics and general relativity, we should be fine to go. Yeah. So, and I'm also grateful to Partha Nandi, who is a NITheCS postdoc in Stellenbosch, to facilitate the connection to Sayantan and convince him to offer the mini school on this really exciting topic. So Sayantan, thank you very much. You know the rules of the game. your slides are already shared on our Zoom screen, and the participants are welcome to ask questions in the Q&A during the talk, and maybe after the talk we can give everybody the right to talk and ask questions in person to Sayantan. So Sayantan, thank you very much for being with us, and we are really looking forward to your lectures. Thank you very much.
Okay, so just a thing. So this is a informal, like not a conference talk. So if at any point you feel like you need to stop me, please stop me. And second of all, the entire syllabus is very amiable. Like the point is that some people might not be very comfortable with some phenomenology of generalized uncertainty principle. Some people might not be very comfortable with the modified gravity. So we will see how to customize along with it. So what I'm going to present, it's probably a good idea to tell that why this big slide is there. That what I am trying to present is that in our group, like I'm doing thesis in cosmology and dynamical system, etc. What George Ellis, etc. has done, I'm trying to expand a little bit. But I have previously worked a little bit in the wormhole, and we have published some 3 papers, which has garnered like more than 100 citations. Actually, it was a right time decision. Not very good, but in a sense that it's still, I'm a little bit proud of this because how should I say, like this wormhole is a very good teaching tool. Like, I mean, like for example, whether it's observationally correct or not, that is a different thing. But to understand GR, it is a very, very good phenomenological. Okay. So this would be the rough outline of the talk. That's a lot. Okay, sir, Parthoda or Professor Petruccio, I would request you to, like, before 10 minutes or 15 minutes, just remind me that, okay, like you have 10 minutes or 15 minutes. So because it's very hard to keep the time. Okay.
Okay,
so,
sure.
I will do so with pleasure.
Okay, no problem. Yeah, so this is I'll first give a brief introduction of the wormhole, then I'll talk about the FQ gravity, where we had much success in this, and then we'll talk about wormhole in FQ gravity, and then we'll talk about the Casimir wormhole. Now, I'm not sure how many people actually know the Casimir effect. I mean, like, okay, physics graduates probably know, but I will try to give a little bit of spectrum, which you will follow in the next lecture. And then I will tell the generalized uncertainty principle. This is almost never taught in, at least in standard graduate course. So how GUP can modify the Casimir effect and how that would affect in a wormhole scenario. And in the third part, so-called this one, we will talk about new modified so-called FQT gravity, which we mostly used with, our group has used with Professor Harko. And then I will talk a little bit about junction condition, like, okay, wormhole is there, but if there is a thin shell, what is the stability? And then I will tell what's the next agenda of my next 4 lectures. Okay. So wormholes are likely like hypothetical shortcuts which satisfies the Einstein's equation. Like, I mean, it's literally like what, it's a very stupid answer, but it gets the job. I mean, like, what is an aeroplane? I mean, aeroplane is things which flies and follows the Newtonian mechanics. Now, a little more standard definition would be that this, okay, so as you know that, I mean, Einstein relativity is like 3 + 1 dimension. There is no way we could embed indeed 3. But if you happen to take only the spatial part, like forget the time one, then it should look something like this. Now, this wormhole and Einstein-Rosen bridge is little different. That I will tell it a little later. But the idea is that there are two holes, and asymptotically it should be Minkowskian, just like the black holes or any solution, because we want something like that, and it should be traversable. What does it mean by traversable in mathematically? That I will comment later part. Okay. And okay, so wormholes history is little fascinating. So I will first go to history. So one is the technical colloquial history, which is given in the graduate one. So as you know that in 1915, the Einstein's relativity was came, and the Einstein relativity math, I mean, what is not the Riemannian geometry we are familiar with today. So those days Riemannian geometry was only curves and surfaces. So Flamm was a well-known mathematician, but he actually figured it out, the Schwarzschild solution. If you do it some trigonometric embedding, just like you do in the FLRW embedding, he could show that there is two different solutions, like in the what today we call it something called causal coordinate, I mean, which I will tell in the next class. The point is that in the Flamm's argument is that if Schwarzschild solution tells that something should go inside, something should also come outside, and he more or less constructed what today we know as like Eddington-Frankenstein coordinate. So Flamm more or less first realized that, okay, something like wormhole can be done. And it was, okay, so I forgot to put the Hermann Weyl's name. Weyl actually figured out that there can be some wormhole, and that I will tell in the next lecture actually. So Weyl's idea was that, I mean, he was working on some philosophical jargon, and he realized that electric field and magnetic field, like so-called ontological duality, this field, if they passes through a hole, something like this hole should be a vacuum solution, and it should have a Schwarzschild geometry. So it's like a field is creating these holes. So this was the Hermann Weyl's idea of this. And Einstein-Rosen first used this as an Einstein-Rosen bridge. Now, Einstein-Rosen was doing something like Einstein thought that, okay, like electrons are fundamentally quantum mechanical. So can I use the electron interaction and tunneling by this to affect the, to derive the Maxwell's equation? So in a sense that he was thinking that, okay, maybe if I define wormhole as a tunnel through which the interaction happens, we could actually make sense of the quantum mechanics. And this is okay. So Einstein-Rosen bridge is a popular term even in like Thor, etc. But that is not a traversable wormhole. I will talk a little bit about later. But roughly speaking, the curves, which the geodesic of the Einstein-Rosen bridge are space-like. So in a sense that if you want to travel through Einstein-Rosen bridge, you have to move faster than the speed of light. And the Wheeler and Misner was first coined the term wormhole. Again, Wheeler actually expanded the Weyl's idea a little bit in the form of that, I mean, if the space, the fields are like the tubes, what should be the properties of it? Okay, now the final wormholes come, like the actual wormholes which we are using. Homer and Bronnikov in the two different paper, as you know, like, I mean, during the Iron Curtain, like both had very little communication, but they realized that in the Einstein's equation, if you play with scalar field, which today we are very comfortable with, inflation field, etc., there is a notion of draining of this, in a sense that they named it particle model in generalized ether flow through a drain hole. That means a scalar field is flowing like a tube. How could we explain this? And then this is the final one which we will use, Morris and Thorne. Okay, so the best history to learn this is the Kip Thorne's book. I mean, there is a book by Kip Thorne about the black hole, wormhole, and time warps. So he actually tells that when Morris was actually done his defending his thesis, he was staying a couple of days in Caltech extra. So that time he thought that, okay, maybe if they write this like sorry, this one, second one, for your tool for teaching general relativity, it would be a very good guide to do that. So they actually wrote it down, and this is where the first, how should I say, first wormhole metric came, which is traversable, and we call it Morris-Thorne wormhole. We'll study only in this one. Okay, now what wormholes are good for? Now, indeed, in the 2020 in the Nature journal, as you know, that there was a wormhole one, and it made quite a bit of stir. So let me tell what they did. So they didn't invented a particle accelerator or some astrophysical observation. What they did is that there is a something called SOIK model. It's called Sajdev-Kitaev model, and this is a very interesting model because in condensed matter it could give you something called non-Fermi liquids, and non-Fermi liquids are almost key understanding of high temperature superconductivity. Now, what is Kitaf's contribution was that he showed that this SYK model is dual to some geometry, like black hole geometry or some other kind of geometry, and so by area CFT duality. And the way they have found is that if I take two SYK model and channel it by some quantum channeling, then it should act in the dual picture, that is the areas dual, they would act like a wormhole itself. So, and the point is that if they use two supercomputers to see how the qubits are sharing, they can actually see that whether we have created a wormhole or not. So this is actually a test that yes, there is an analogous wormhole in the condensed matter in the quantum computing one. So this is a one, and this has created some stars like whether it is actually wormhole or because there are lots of dualities are involved which are not conformally invariant, etc. But this is a thing that it is interesting to study. Okay, now what should be the rough criteria of wormholes? Again, these criteria are like guidelines. I mean, of course, we will violate most of them, but in a sense that matrix should be spherically symmetric and time independent. Okay, again, it is not exactly true. You can have curved wormhole also, rotating wormhole also. Again, solution should satisfy Einstein's field equation. That is the two Einstein's field equation, and then the throat which is connecting the two flat region should be, I mean, how should I say, like it should be asymptotically flat as r tends to infinity, and no horizon should exist. So when Carl Sagan actually asked the Kip Thorne to actually write that whether there is a wormhole or not for his contact book, the point was that Kip Thorne said that you do not want to send our heroine to the black hole because black hole is a one-way membrane. So that is a stupid way. So in a sense that phi r, which is the shift function which we will talk, it should be phi type, and the tidal gravitational force should be low. How to get the tidal gravitational flow, we will talk a little bit. And wormhole should not have like the infinite redshift. So in a sense that when traveling through wormhole, people should take finite amount of time, just like the falling in the black hole takes infinite amount of time because the redshift goes infinite at the horizon. And again, matter fields which creates the wormhole should be reasonable. Like, I mean, we want to engineer something. Okay, now wormhole in the modified gravity was started first by Lobo and then the sausage. And my guide actually proposed the first PRD version in the FRT gravity, and Harco logo later extended in the various modified gravity. Now, what is the advantage of modified gravity in the wormhole rather than the normal? That you have to wait for the next lecture, because the problem is that in wormhole you need something, the violation of null energy condition. Now, modified gravity can actually bypass that a little bit. Now, how this happened, that I will tell in the next class. That is the Roy-Choudhury equation. You have to juggle with Roy-Choudhury equation. And in the FQ gravity, first work was done by the Geminis. And then in the FQ gravity, the later like Sanjay Mandal, who was my senior, and Pikesha, who is my guide, they later extended in the cosmological constant. Cosmological constant, like you can explain the lead time acceleration in the FQ gravity, which is very consistent with the data, like Pantheon data and Hubble data. Okay, now, okay, so let me maybe start with this. So the point is that if you remember your first course in GR, that is that you take the two conditions, like the connection is like there are two tangent space and you are giving a prescription from two tangent vector, one to another. Now, how to do so-called the parallel transport or the connection? You consider two conditions. So one is the torsion one, that is the Cristobal symbol should be symmetric in the two indices, and the metric compatibility. So what happens if you drop the metric compatibility? You get something like this. So you are parallel transporting as well as the length is increasing. So just like the dot product, it itself is better. So for this, the best is the so-called the Kanakata. It's a 1000-page big modified gravity conference proceedings. So this has all these good pictures. So this is the rough idea of the so-called the Q or non-metricity of this. So Hermann first again proposed this to the gauge theory. So in the gauge theory, he realized that if he allows the so-called the A, which is the vector potential, to move like that, he can actually explain the electromagnetism from the general relativity itself. And why he was abandoned or why Einstein didn't take it seriously, that I will tell in the next class, so-called the problem of two time. What is important is this picture. This picture actually shows, sorry. So this picture actually shows that this FR, our R, that is the curvature based typical Einstein-Hilbert action, T, which is the teleparallel gravity, and this is the Q, symmetric teleparallel gravity, or are equivalent in the linear order. Now, okay, so the point is that, as you know, that GR has tensorial 2 degrees of freedom, vector degrees, tensor degrees, and the total 10 degrees, the 2 degree of tensorial degrees. So that's why in the gravitational wave, you typically takes like transverse traceless gauge to make sure that it is only accounted for 2. And these counting are much more difficult, but it can be shown that these all are equivalent in the linear order. Now, one might think you might be a little uncomfortable is that, sorry, just a second. Yeah, I have defined Q as a first derivative of G mu nu. So that might be a problem with principle of equivalence, right? Because the point is that principle of equivalence says that the first derivative of G mu nu, we can always take it to 0, right? I mean, that's why we need the curvature base to start with. So how can I write the Lagrangian as a first derivative of Gij? Doesn't it violates the principle of equivalence? The answer is no. The point is that this is related to R and Q is related by a boundary term. And this boundary term you can always take in the action, as you know, in the Lagrangian, you can always drop the boundary term, provided that it is Minkowskian flat. There are situations where you cannot drop the boundary term, as you know that it's called Hawking-Gibbon-York term. But in our case, as because we are working the flat Minkowskian limit, we can always drop the boundary term, and that's what the boundary term would have the second derivative information. So this is indeed true. Then we use this itself. So this is the Einstein-Hilbert action, the one, and the point is that FQ, when it is Q, would give the Einstein general relativity, because we always have to go back to the Einstein relativity as soon, I mean, in the limit, just like the Einstein relativity has to go to the Newtonian gravity. Yeah.
I had a concern. What is the Q factor? Q is a scalar or something?
No. Q, that I'll come. So Q so far is a three tensor. The construction of Q scalar is little complicated. That I will come later. Yeah, just like the
So what is the properties of this rank 3 object? Is it symmetric under? I have seen that
symmetric
it's
under
symmetric
mu nu.
under mu nu.
Yes,
Okay.
symmetric under mu nu, and the point is that this is calculated under some suitable gauges. So if you want to calculate Q from the first principle from the metric, you have to calculate something called the L conversion.
So I would like to understand in a standard Einstein-Hilbert action, it is basically gauge invariant object because it depends on the curvature scalar. But in your case, whether it is a gauge fixed version of some gauge invariant action?
It is a gauge fixed version, and that creates a problem if you try to calculate the black hole entropies, because this boundary, this takes a lot of gauges. Yeah, so that is a 2. And in fact, the gauge counting is given here. See, so 10 plus 4 diffeomorphism, and due to boundary, there are some gauges. Then you get the 2. Not that your typical like the vector and scalar curvature, scalar perturbation are taken care of.
Okay.
Yeah. So yes, it is a problem that if you want to quantize it, the FQ gravity, you will be in horrible trouble, because the point is that due to the extra gauge redundancy, you will get more Ghosh than expected.
I understand. Okay.
Yeah.
Thank you for your clarification.
Sure. No problem. Okay, so as Patsara was saying, that how to get the Q scalar. Okay, so the point is that given the Q, this is the definition, we define something called the superpotential. Nothing to do with the supersymmetric superpotential. I mean, that is like the Dirac equation, superpotential. This is a superpotential in a little colloquial way. I mean, this is the space of all potentials. Okay, and then there are two different contractions, and we would use so-called the Penrose notation. And the reason for this is that in the typical general relativity or Riemannian metric, you do and how to get the final scalar out of it. And this is the formula for the final scalar, given 8. How to calculate the PUQ? It's
It seems that sometimes we lose the connection to Sayantan. Maybe Sayantan,
Yes.
if you can hear me, maybe switch off your video. Maybe the connection is not so strong. Sorry, participants of the meeting. I'm not sure. Let's hope that Sayantan can gain the connection again quickly. Now he's gone completely. Let's give him please a minute to see if we can join again. Please stay online. And maybe Pata, if you have WhatsApp communication channel.
Yes, I have already communicated to him.
Maybe we can see whether we can join again.
First.
Yeah, no, thank you very much. So please, attendees, be patient for a minute. Here we go. Wonderful. Sayantan is back. Sayantan, I think we lost you for a minute or so. Maybe switch off your video so that we keep the bandwidth small.
I think that would be a better idea.
That's perfect. Thank you very much.
Yeah, sure. Okay. Sorry. Actually, the point is that in India it is raining too much, so like the getting power.
Okay, I'm sorry to hear that. Sorry, and it's far away. Yeah. Perfect.
So screen is shared, and this is done, and this is the present. Now we are back. All correct?
Now we are back on track. Perfect. Thank you very much.
Yeah. Okay. Yeah. Sure. Sorry for the inconvenience. Okay. So this is the monstrous looking field equation, which we have to tune it somehow. Okay. Now how to take this? Okay. So far so good. And now we are getting the so-called the 12th number question. 12 number is the equation. Just a second. Yeah, 12th number is the Morris-Thorne metric, and this is the phi, which is a redshift function. This BR by R, why it is taken is little difficult to tell without the motivation. The rough idea is that you, at the Schwarzschild level, you want this to be a constant because it is 2 GMM by R, right? So in a sense that at least local charts, so-called the local atlas, you should always get like a metric in this form. Now, what are the conditions BR has to satisfy? Okay, like given any function, you can always bring it like this. This is a little interesting. So at throat, BR equals to R0, because remember Einstein's equations are integral equations, differential equation. So when you integrate, you have to get some initial condition. Just like in the Schwarzschild one, you give the mass by your hand. So, and the second thing is that so-called the flaring out condition. So-called the B prime should be less than 1. And this is a little ugly looking expression. Why this ugly looking expressions come? That I will tell in the next class, that why such a thing actually denotes the flaring out conditions. And the point is that the asymptotic flatness condition, which is reasonable because as R tends to infinity, we want this to coincide with the Minkowskian space. Okay, and this is the T mu nu. Remember that my metric is always minus plus plus plus. So in a sense that in the T mu nu, so called the isotropic fluid, anisotropic fluid rather, R and T always takes this form. So this is a complicated way of writing like the rho PRPTTT. Yeah, and if you do the calculation of Q, the prescription I have given, it is a very big calculation. The Q as this. Now our job is done. Okay, now in FQ we have taken a typical linear model because the non-linear model doesn't get solved, and there is a second reason also, because if you look at the last equation, the equation 11, it actually forces the F double Q, I haven't loaded, because of the superpotential to be 0. So if you take a particular gauge which is called coincidence gauge, you are forced to take the linear form. Now I know it might sound a little stupid that the beta is like cosmological constant, alpha is like your so-called 8 by g by c to the power 4. The reason for this is that we are taking this model, forgetting about this, and check that whether our alpha, when we get to the realistic one, does produces something or not. So in the last paper which we have done, we will have actually taken a non-linear model, and I will show that how monstrous like the equations are. I mean, it is like reasonable. So for now, we will take this model, we will calculate the 14, and we get our field equation. So let me just go to the field equation first. That's 19 is the row equation, the 001, and PR is the 1 component, and PT is the 2 and 3 component. Okay, so this is our beloved field equation. Now we need something, the concept of energy conditions. So what happens is that, so one of the question one can ask that why isn't every metric like a solution to Einstein's equation? I mean, at the end of the day, you are putting a metric calculating G mu nu and call it the T mu nu as same as the G mu nu, and you call it your own metric. The reason for this is that given a reasonable metric or reasonable T mu nu, it has to satisfy some conditions of energy conditions. Now, what is the origin of this energy condition? Unfortunately, I cannot give a satisfactory answer if I do not introduce the Roy-Choudhury equation, which I will do the next one. But roughly, you can understand this. These energy conditions are the conditions which, what say in the Newtonian equivalent of what is the plus sign of, like, I mean, G by R square. Like at the end of the day, by some reasonable approximation, you want the gravity to attract each other, not like the repulsive. So in a sense, these energy conditions are the restrictions of the T mu nu, which ensures that gravities under some colloquial language are attractive. Out of this, the null energy condition would be important. Why? I will tell it later. Okay, so this null energy condition, so this every energy conditions are taken like Tij, Kij, and K is a null vector. So as you know, for the null vectors, you can always write like -1 and R as 1 in some inertial reference frame and get that rho plus P greater than 0. There is a little bit problem with the wormhole construction itself, which is figured it out by one. So look at this picture. So let's say some light rays are coming from down and it is going diverging. How can this happen? Because the light rays, if there is a mass at the throat, should always converge, right? I mean, the sun converges the light rays. That is how the Einstein's relativity was proved. How can
I want to ask a question. What is the difference between U and V for vectors?
Oh, no. It's nothing. Yeah, so the point is that you need the proper sign like rho, P and T, like if you write it the diagonal one. So the V's are taken as the unitary space-like vector. So the T mu nu is just a way of writing in, how should I say, in a tensorial way, like covariant way. So it doesn't reflect like a particle is actually moving at a space like. The point is that if you want to take, okay, maybe I can take this one, just a second. So, yeah, so, okay, you can see me if I am drawing, right?
Yes.
Yeah, so the point is that it's just a way of writing P, PR, PT, and PT. That's it. The way you write it is that you actually take the delta, the PTT part, then you take the plus part, that is rho plus PT again. Now, because you have to subtract because you have too much PT, you have to subtract this. That's why you take with a minus sign.
Oh,
so
okay.
It has nothing to do with the one. So it is just the matrix which is written in this.
Okay. I understand.
Yeah. Sure. Okay, so maybe I can, now that I am in the one using, I can tell it from here itself. So if there is a bunch of lights which are coming here, the point is that around the throat, it has to diverge. But light do not diverge. Like, I mean, if there is a massive object, light will always like to converge. So how to make this diverge? And this is unfortunately can only be done by Roy-Choudhury equation. So if you know that some bunch of light rays, so-called the 9 Roy-Choudhury equation, is equals to like half of theta plus some rotation part and the shear part, which you can take it 0 for radial, and then the R mu nu part, R mu nu, U mu. And this would require that when theta dot is greater than 0, that is that at the throat we want the light rays to diverge, this would ensure that the null energy condition, that is the T mu nu, K mu nu has to violate. So this is something which has bothered Kip Thorne also quite a bit. So there is an interesting story, I will tell it later. So Kip Thorne, after a lot of hard work, figured it out that in the throat the null energy conditions has to be violated, and after he actually published it, so then Don Page immediately cited that in the Hawking Alice it is already done by the Roy-Choudhury equation. So yeah, so the point is that, so in a sense that in order the wormhole throat to be stable, we have to violate this NAC. We'll see by what exotic matter we do. So again, violating NAC is that rho plus P less than equals to 0. Now, as you know, for all ordinary matter, rho is definitely greater than 0. P is also greater than 0. For cosmological purpose, we take P to be equals to 0 because of the rho is too high. But the point is that how to get this less than equals to. The answer is so-called the Casimir force. Okay, so Okay, so I am about my half time of my talk, right? Roughly, or a little less than half time.
It's almost, it's a half time.
Okay.
Most
Okay.
perfectly half.
Okay. So, okay, I mean, maybe we can just speed it up and speed it down when to do. The Casimir plates are very interesting. The point is that if you solve like SHM, okay, it's probably better if I take this one, I guess. This is a little bit. So everybody is okay if I use this one, because then I can actually draw here itself.
Yes, I am fine with it.
Yeah. So in the presentation mode, I cannot draw. So the point is that in quantum mechanics, as you know, that the ground state is given by half h cut omega. In the quantum field theory, you take that there are infinitely many harmonic oscillator, and you take like a dagger A for all the k components. Now the point is that what happens to the vacuum energy? There are infinitely many half h cut omega. That should be infinite, right? That is the so-called like ultraviolet cutoff, or like the infrared cutoff. Now, how to prove that the vacuum has infinite energy? And this was provided by the Casimir, that if you take two conducting plate in a very thin one, then the modes would be, because of the SHM, the modes would force these plates to attract, because there are negative energies because of the half h cut omega, and this negative energies gradient would include the force to attract. So this is the Casimir energy. So, so you both know the little bit about Casimir energy, right? So I can skip a little bit to the theoretical part, right?
Yes.
Okay, so the point is that how to prove the Casimir energy. This is done. Okay, so there are many ways of doing this. My most favorite one, the Casimir actually did, Casimir and Lifshitz did by the typical the quantum field theoretical argument, and Lamarck actually prove it. And this is how to find the Casimir effect. How to find this formula, I actually prefer the Padmanabhan's book. So in the Padmanabhan's book, it has been shown that if you take the 1 plus 2 plus 3, etc., the so-called the zeta minus 1 is minus 1 by 12.
1 by 12.
Yeah, popular Ramanujan joke. You can actually show that this is actually true. Now, why? And this is actually related to the so-called the zeta hypothesis, that the Riemann zeta function is not valid in the complex plane for zeta greater than 1. Then how does it even make sense to talk about all the roots are in the complex half? The reason for this is that what Riemann hypothesis tells that not all the zeros of the zeta functions are in the half. It says that the analytically continuation zeta function, which is a completely defined zeta function, has this. So if you take this summation, make it as zeta minus 1, and analytically continues this zeta function to something, you will get the minus 12. So this is a very good one, that one experimental proof that, I mean, the zeta regularization itself works. The standard one, you probably know that this is a trick known as the Pauli-Villard regularization in the quantum field theory, which uses this. Okay, now this is the field equation as promised, and this is the T00 part, and this is the T11 part, and this is the T22 and T3 part. I mean, yeah. And now how to get this? Now, for the Casimir energy density, this is the technically done, that this Casimir one actually can, if you put it back, like in the first equation here, and solve for the B, because remember FQQ is 0, because we have taken the model as the linear model, you will get the shape function to be this. This was done before us also, like it is not that. And Gariti actually first did that, what happens this. And from this, once you find the B, you plug it back to B in here, and you find the rho R and PR and PT, and you get the PRPT equation. Now you take
I had a question.
Yes.
Whether you are using the Casimir effect for spherical shell, what is R?
No. This is not spherical shell. This is for the parallel plates. So that's the catch we'll talk about later. Like
okay.
The point is that they say that somehow you are getting the Casimir energy, and this could somehow, in principle, charge the throat. So point is that you are taking the Casimir energy as the A fluctuation. Then here you take the swindle that A equals to R. I mean, this is actually Gariti, if you look the fine printing, this is actually written. So it is given that why A equals to R. So Gariti gives a little bit of standard argument that for parallel plates, what should be the T mu nu for parallel plates? So he actually used the Dirac delta function for two parallel plates. to calculate the Dirac delta and show that if you want that T mu nu to identify the T00 as rho, you have to identify A with say R to the power 4. So it's a little convoluted argument. So I request you
No,
to.
that I understand, but what is the original interpretation of R? R is what? R is initially appear in your Einstein,
No.
your energy
R is
momentum.
the metric. So R is literally what Schwarzschild's one. So R
Total
is
radius.
yeah, no,
Yes.
not Schwarzschild one. R is a general, how should I say? R is in the spherical coordinate. R is the radial distance.
Okay.
Yeah, I mean it's like asking like what is R in the Schwarzschild metric. So
Okay,
we have
but
the
the point is, but the point is that in your case you are using spherical symmetry.
yes.
So your geometry, if you fix R for a constant R, your geometry is basically the spherical shell.
Yes.
So how you reconcile the parallel plate, distance between parallel plate with the distance associated with the radial coordinate R?
Yeah, that's why you cannot. I mean, that's why we made our paper in the, sorry, it would come a little later, with the cylinder and the sphere. So you cannot. The point is that it is a, Garit's swindle was that, lastly, okay, take the Casimir energy. Do not ask the question that, I mean, how did it came. If you take two plates like that, you hope that some wormhole, which is in the R, okay, sorry, A is not R, it is actually throat. So R naught is well defined.
Okay.
Yeah. So it is in the throat they are putting the shell. So this system they are putting here. So at the throat they are putting the shell. So they can identify this A with the R naught. Now they are not bothering about the geometry and they are asking that, okay, now if I put it like that, can I get a wormhole in the F2 gravity or not? Does it violate the
I understand your strategy, but you know that there is a big problem with the Casimir effect on sphere.
Yeah, that we will tell. I mean, how to bypass that.
Problem. So whether you are bypassing this situation somehow?
Yes, so that would be our research. So this is already done by the Garitini, and this would be our research, which I will tell that how we somehow bypass.
Okay. Okay, yeah. Fine. Okay.
Sure. So this is the shape function. Again, look, given a shape function like any colloquial, etc., you just have to check two things: whether it is asymptotically going to 0 and the B prime is less than 1 or not. Because we told that flare-out condition is B prime is less than 1. And this is B by R tends to 0 at R tends to infinity. Now, if B goes to 0, then of course B by R will also go to 0. So that is not a problem. Yeah, so we get that. And now the NEC, why we take the rho plus PR? So this is a very good article by Visar and NITheCS that I will tell later. The point is that when you are taking like the null geodesic in the throat, you are only considering the null geodesic, not the twisting or one. So in a sense, in the T mu nu, only the rho and PR would affect because we are only considering the U mu nu as something like -1, 1, 0, 0. So this has been shown by the Matt Fisher and NITheCS paper. I mean, this actually Sayantan, Matt Fisher and NITheCS paper. That they have actually said that the null energy condition actually needs to be violated in the radial one. So I am not going details into this because that is the work in the next lecture. So, but I will actually in the last I will tell what are my papers does and then I will go. Okay, so I will now tell how the Casimir one. So in the Casimir one, if we put it this end and then take A as R, then it is a much better geometry. So before that, okay, so these are typically done in the mathematics department. People do not bother about the Casimir effect, etc. Fortunately, I come from the physics, so I realized that, okay, if you change the geometry a little bit, you can do a little good. Now, the first question was that, has it been done? Like if I take two parallel cylindrical plate, can I tell that what is the Casimir force to that? I mean, because it would be nightmare to do that. Fortunately, this is the big expression where length is the cylinder length, A and B are the inner and outer radius, and gamma is the one. So if this is A, this is B, this is L. This is the one. Now you can automatically see that why spherical Bessel function comes. Like if I take ask you to do a Jackson problem in electromagnetism in the cylinder, you would have to get the Bessel function. Just like if I ask you to do in the sphere, you will have to invoke the spherical harmonics. So this is the very complicated expression. We have cited that where we got that. But the point is that this could, in principle, give us the answer that what is the Casimir force between that. So they just counted all the normal modes in between this in the spherical region. And this is the energy expression you got. And we have tau. Okay, we cannot keep on adding this. We have to use some approximation. We have taken the A is much smaller than B, some practical application, practical reasons, and we got the expression like this. Okay, and this is the volume we got. So the energy density, we got it there. And this, again, we have played the same game. The rho is known for the field equation, the 0, component. We calculate the shape function. Okay, the shape function is very difficult because again this is a one, but what is we are proud of that this is exactly solvable. Like there is no numerical recipes there, etc. And exact solve models are always good because like you can always plot without worrying about this. Again, the shape function does indeed go converges to 0 as for even wide range of parameters, as well as the flare out condition, that is the less than 1 criteria, is also satisfied. So yeah, we are happy. So PR and PT, if you put it, it is very like complicated expressions, but again it is exactly solvable. Now the NEC, that is the rho plus PR, as we told that why the radial part is only matters. This is this, and see how the NEC does. Voila, this actually is less than 0. So we have actually constructed that for cylindrical geometry, as Pathoda was saying, we are actually getting the viable wormhole. Now for the sphere, now the instant lucrative option would be like 2 concentric sphere. Fortunately, this is done. Like what is the Casimir force between 2 concentric sphere? The problem was that how to fit wormhole on inside that. So we realized, I mean, when I was collaborating with my like senior, that if we take 2 sphere in d distance and find the Casimir effect, then we can take it. Now the point is that with 2 spherical plates which are not concentric, the Casimir force is like horrible to calculate. Now some condensed matter physicists actually did something like that. So the point is that how do you do such a problem? Like if I ask you like the 2 weird looking shape and find the Casimir force out of some approximation. Okay, so they use this, that they have found some of the modes and they use the so-called the multiple scattering method, just like the Feynman diagram. So they did. So the first mode is giving 1 interaction, second mode is taking 2 interaction, third mode is taking 2, and then they use something called a random phase approximation to get approximation 1 for this. Now remember, this is horrible approximation. Like D is much greater than A, which is the distance should be much greater than the radius, etc. But at least there is an expression for that. Now there are now 2 free variables which we have to deal with. We have taken two cases. So actually initially we have taken that as because the radius was, I mean the distance is the only thing that matters for the throat. We will keep the D as 1. Then the reviewer at EPJC actually asked that no, you should for completeness take both the cases. So for the first case we take the D as variable, A as constant, and the second case we take the A as variable, D as constant. We get the rho, we get the volume as roughly cylindrical, we get the pressure. And for the first case, this is the big B, and for the second case, and B prime is again less than 1 in the small range. For the outer range it is going up, but again that is out of throat, so the expression itself is not valid, no longer valid itself. So at least in the throat this is done. And for the NEC criteria, this is the NEC criteria, you can see that it is still less than 0. So it is the NEC criteria is also violated. Now for the second case, when A is variable, D is constant, this is the shape function. K1, K4 are very complicated expression. You can welcome to look at the original paper. But the good thing is that again, it is exactly solved. Again, B prime is coming less than 1. And the NEC is actually coming to be like the, sorry. So this NEC is positive. Now, why is that? The reason for this is that the NEC is not always needed to violate. And the simple reason is that the Roy-Choudhury equation only cares about the R mu nu. So in a sense that in your modified gravity, if you have some R mu nu plus something for FR or something, what Lobo etc. is done, it does not needs to be violated. So in a sense that in this case, we are not violating. But again, on the other hand, if it is a modified FQ gravity, we cannot expect that. So yeah, I mean, at least it is whatever it is. So now I'm moving into my second paper in GOP. So is there any questions or something? So should I have like about 15 to 20 minutes, right? If I understand correctly. Patsuda?
Yes, you have.
Yeah. Okay. So now I am going to the, okay, so this is based on our first paper in the like EPJC. This is a second paper which is based on, we more or less wrote the same time, but it got published after 1 year. So the point is that why bother about changing the Heisenberg uncertainty principle? It is a very good equation which we learn in the quantum mechanics. The problem with this is that, okay, so why there is a better reason for that? I'm just giving that why, at least in phenomenologically you expect. So in near x tends to 0, this behaves like this. So x as 1. But in the Schwarzschild solution during the event horizon, it should behave like this. Now, again, I'm not saying that this is a crystal clear answer. The better answer comes actually from the string theory and the loop quantum gravity. Sorry. If you take the beyond tree level diagram, you would actually get something like this. But I'm just saying that why, like as a guarantor, why we should expect such a thing. Now, if you want to take x which at near behaves like the normal one, but at the say singularity, it works like delta x equals to 2g delta p. You see that you have to change your modified so-called the commutator like this. So this satisfies this condition. Heuristically, at least, h cut delta p for less than for much further we want the quantum mechanics, and for the Schwarzschild one we want the semi-classical gravity, the gravity as semi-classical, we want this. This roughly solves with a quotation the problem. Okay, now this is a very good book, review article in the by Hosselfeder, where it tells that why even in the string theory and loop quantum gravity also we get a very similar thing. Okay, now any parameter is worthless if you cannot at least give a phenomenon. Yeah,
I had one question.
sure.
You are arguing that you are suggesting a minimum uncertainty in position, and this minimum uncertainty in positions can be achieved from some deformed Heisenberg algebra. But how could I say that, or how could you say that this is the, I mean, we should have some deformed algebra which can propose some minimum length scale, but how could I figure out the explicit structure of the algebra? You are saying that it is a deformation in the Heisenberg sector, but why? Why you are not bothering about the other sector? That means the XX algebra, PP algebra. I mean, what about the fate of the position, commutator, momentum commutator?
Yeah. So the point is that it is already done. It is in our second paper that if you take the xi xj, that is so-called the non-commutative geometry, as you also know that the Sunanda sir also does. The point is that yes, this is a theta ij. The point is that the non-commutative geometry, the position, I mean, doesn't requires immediately from the Gedanken. So in a sense that if I give you this is like the standard one, there is no as such reason you can tell that the xi xj doesn't has to commute. So the point, that's why the so-called the non-commutative, the original motivation, I mean, I might be wrong, you can correct me, is from the string theory. In string theory, the d branes, when moving into some like the conformal one, there the boundary, the Neuhaus-Schwarz boundary condition gives this.
Boundary condition, yes. But I think this is not, I think string theory is not the fundamental reason. I think the point is that when you combine quantum mechanics with the Einstein general theory of relativity, then there is a problem, because if I understand that when you make the uncertainty in the position is so small, then it can generate the huge uncertainty in the momentum sector. And the momentum sector, if you connect it with the energy, then it will generate the huge uncertainty in the energy sector. And since you know that the energy momentum can generate the geometry of space-time, then you can invoke some additional quantum fluctuation in the space-time geometry. That is why you can not propose some smooth space-time manifold. Then you can consider some discrete nature of space-time. But there are no concept. We don't need to introduce the concept of string theory as such. This is just a intercast marriage between quantum mechanics and general theory of relativity.
Yeah, but point is that again the point would be like, I mean, at least there should be one fundamental theory which I can say what's called the theta ij. This should actually be calculated by some microscopical principle so as that I can go with it, right? So similarly, I am saying that in the Husserl data, this lambda, the parameter is can actually be calculated by the first loop correction of the string theory as well as the in form theory, the loop. So yes, you are absolutely right. Now, why I am little bit biased with the energy position momentum, not the work. So first of all, we have a paper we just published. We just submitted it yesterday. The point is that with the non-commutative geometry, as you know, but the point is that here in the wormhole, I am only bothering about so-called the semi-classical region in the so-called the horizon, where like the Hawking interaction itself. So in the semi-classical region, there is not as such, I cannot see like why in the semi-classical region you need the xi xj non-commutator. Because in the semi-classical, you even if you start with the string theory, so-called the Buffer-Strominger entropy calculation. Book kya hai? Time.
Sorry?
Yeah. No, sorry. Security. Okay. So the point is that so just like the Buffer-Strominger one, so that in the semi-classical limit as well as in the string theory, both in the event horizon gives the correct answer. So I am saying that this is GUP is much more little bit fundamental than the non-commutative, because the GUP you need even in the semi-classical region. So if you see this argument, this is a semi-classical region, right? Because I am using the Schwarzschild one, because in non-commutative geometry we do not even know like whether the space-time manifold how to take it. I mean the Konas etc. has papers, but
yes,
like,
I agree with you. If you believe on semi-classical approach, then it is okay.
Yes. Yeah, so that's why the point is that our wormhole actually bothers about the semi-classical, but fortunately I will talk a little bit about the non-commutative also. I'll talk a little bit about like, okay, you and also you probably know Sunanda sir actually works on lot on that with Sayantan Ghosh. Yeah, I was supposed to join the PhD under him. So I also happen to know a little bit, but I will tell that how one uses the non-commutative in the wormhole context also. That is my senior's work, but I have mostly focused on the GUP one, and the advantage of GUP1 that it is exactly known that what is the effect of Casimir effect in the under GUP. Okay. So, and the second thing is that the GUP changes the dispersion relation fundamentally, and there is a very good phenomenological bound. Okay, sorry, all these things would be minus, but the point is that if you want, okay, what is the bound on the lambda? Give me some experimental bound on this. So this is a very good article by Surya Das in the PRL, which has actually shown that by the lambda shift or the Landau level or by the tunneling, what could in principle we can use the tabletop experiment to probe the lambdas. And there are other Kipthon and Camellia, they have published that if you do the gamma ray burst, you can actually see that how speed of light is changing, and from that dispersion relation we can give this. And from the gravitational wave also, like you can actually put it, it is given by Robert Munn. So as you know, Munn is one of the founders of this generalized uncertainty principle as well as the non-commutative geometry, all this. So yes, so the point is that this is phenomenologically sound. Now, how to invoke this in the special one? So every xipj can be written like this. Why it can be written like this? Because we want the irreducible representation of SO3. The irreducible representation of SO3 can already be written in the scalar part and PI part, not PI part, because we want the symmetricity of the original, so-called the Heisenberg center, to be preserved. Now, if you take this, again, remember that when f equals to 1 and g equals to 0, we get our normal Heisenberg principle. Okay, now, from the tadpole and fish diagram, so you might be wondering, so how one does the quantum field theory with this? And this is in the
I had another comment.
Yeah, sure.
Can I ask some?
Yes, please,
if I understand, can you go back your expression of algebra of position and momentum? Yes.
This one.
Yes. Just down. Yes, this one. I think that you should make it a full screen. Otherwise, it is just a problem to look at the. Yes.
Tell me the equation number.
Yeah, I can't see the equation. Equation 44. Yes.
Yeah.
These equations, in your case, if you consider G and F are arbitrary function of P square, then if I ask the question, what is the fate of xi, xj commutator, pi, pj commutator? I think the standard commutative coordinate and commutative momentum will not consistent with this equation 44 because they will not satisfy the Jacobi identity. If I understand correctly.
No, that's right. Okay, so from a mathematical point of view, f and g are not
G is an
fundamental.
arbitrary function.
No. This is not an arbitrary function. No,
Okay,
that
so what
I will tell. Like, what are the f and g? So, just to give us, this is one of the choice f and g under some mathematical one, so-called the maximal localized state, and the second one is so-called this is the f and g for variation method. No, these are not arbitrary. So you are right.
Okay.
That, so the point is that I can go even further. Like, I can say that if you take arbitrary f and g, even mathematically it would not be a Hilbert space, because in the Hilbert space you need all the Cauchy sequence to converge it, like something like that.
Yes.
The point is that it might not be even a Hilbert space. Forget about even physics. Like, even mathematically it might not be consistent. So no, f and g are not arbitrary A1.
Okay, if the point is that if for a given, if you start from some Heisenberg algebra, which is deformed Heisenberg algebra and supposed to be algebra with respect, which can be realized in a particular Hilbert space, then the position non-commutative, the position commutator and momentum commutator can take any arbitrary forms, I think. I mean, if I ask the question, what is the nature of other commutator for this particular equation?
For other commutators, I would say that in the position sector, I didn't touch. So I didn't touch. So xi, xj would be 0.
Is it 0?
Yeah. So that's why in our generalized uncertainty principle is not non-commutative.
Okay.
So that's why, I mean, I am, okay, so in the previous one, so let me just drop. So I am just generalizing this one dimension one to 3 dimension.
Okay.
So this I am putting f, and this p square becomes
but,
pi.
But my concern is that whether this choice of this commutator will satisfy the closeness of Jacobi identity with this commutative coordinate and commutative momentum. What is the fate of Jacobi identity for this choice for 44?
The point is that Jacobi identity is only true, like, I mean, if you want a Lie algebra, you can have a non-Lie algebra also, right? I mean, not everything has to satisfy the Jacobi identities. Like, for example,
if you consider an algebra, okay? If you consider this, and it's first of all, it is an enveloping algebra, enveloping Lie algebra. So
I didn't say that it is a Lie algebra.
No, it is an
enveloping algebra. Has to be,
yes. But the point is that Jacobi identity must be satisfied, because if you consider the algebra is associative, if you lose your associativity, then okay. But I believe you should consider the associative nature of the algebra, whatever be the fate of Lie algebra.
Yeah, I'm not sure that, I mean, okay, well, maybe it is my...
You follow my concern. Jacobi identity only tell us the associative nature of the algebra before making it a Lie algebra. Because Jacobi identity is most fundamental. It is not depends on the structure of the Lie algebra. It is just to be a algebra is an associative algebra.
So if I put, like, say, xi, pj, xj, that is again the cyclic sum, that is the xi, xj, pj, and then again like the p, x, xj. So it's satisfying the Jacobi identity, right? This is 0 because I am not.
If it is 0, then it is satisfied. But for this,
so it seems like it is satisfying. Like, I mean, just this calculation roughly shows, like,
no, I think no, because if you just consider xx and if you actually, I am seeing that
they take the commutator itself, so the delta would commute with pj anyway.
You see, xp commutator is a function of p, and you are writing down the nested commutator, so it is a commutator of xp with x. So x is and p is not a trivial. So how could you say this is 0? You follow? Xp commutator is a function of p, some polynomial of P.
Yeah, that's what I'm actually trying. So if I take, let's say, xi pj commutator, then pk, then I take, say, pk xi, then pj, then what should it be? Pj.
No, I think it is just, it is not correct. So you are follow the cyclic permutation. So it is
Yeah,
xi.
cyclic permutation I'm following.
Yeah.
This is correct, right?
No, everything is not the commutator of px. You are writing everything is a commutator of x and p. It should be commutator of xx, pp, and xp.
No. Xx, I am saying that it is it is commutative geometry. So all the xi, xj commutator for me is 0. All the pi, pj commutator for me is 0. I'm saying
Whether
that
whether this choice is consistent with the Jacobi identity.
yeah, that is what I'm saying. That it looks like it is, because if I take xi pj, I'm getting delta ij plus pi pj. So pi pj.
But
Commutative with pj. This
yeah,
again.
this
Yeah.
is 0, this is 0, but this last one, this third term will not be 0.
Yeah, pi. This is pi pj. This is 0.
pi. Okay.
This term and this term is the opposite, and this term is trivially 0, because as I have taken the xi xj to be 0, so pi pj is also 0.
Okay. Okay, fine. Okay.
Yeah, I haven't checked it. I mean, but I mean, again, like the Man's paper probably, I mean, Man is a very big shot. So yeah, I mean, thanks for pointing out. But I think that that's how they have chosen this form. Like if you take a little more than that, I mean, yeah, like 3p or like single p, then probably the so-called, how should I say, like the Jacobi identity might not be there. But here it seems like it does.
Okay.
Yeah, because the xi pj, this is the pi pj pk. So again, you can put it like pi, then pj pk, and then so again, like pi is commute with each other. It is. Oh, okay. Sorry, I do not have to do. All of them are 0 because pi is commute with each other. Okay. Because this is a pi pj, right? So pi pj, I am commuting with pk. So each of the individual term pi of pj pk plus pj pk pi, all of them are individually 0. So it really satisfies Jacobian identity.
Okay, fine.
Yeah, sure. Okay, so the point is that you can actually write a quantum field theory based on this and calculate the first loop correction that Red Bull and Fish about all this to get the show that this is ultraviolet safe, because there is no point of suggesting a new type of GOP if you cannot even ensure that it is ultraviolet safe. Okay, now problem is that this is done only for the first loop correction, and the point is that higher order loop, it is ultraviolet or not, that nobody knows. I also do not know. So but point is that at least in first loop we are now this is how should I say, sorry, yeah, this is the wave function we will study to get what is the bound on f and g. Okay, so this is the wave function we do. And now there are two schools of thought, actually three. There is also called model 2, but we mostly follow the standard 2, the KMM and DGS. And the point is that given this relation, there could be a very much f and g, right? And they found out that what it has to satisfy, it has to satisfy that it is a Hilbert space. So in a sense that it is in the L2, like the Cauchy sequence in the inner product is convergent. And the second thing is that it has to be completeness. I mean, like say the outer product integration should be 1. Now with this, with a little bit of trickery, they found out, KMM found actually given that this prescription, honestly speaking, I didn't quite understood, because this is very, very hard in mathematics. But roughly, actually, once they calculate, they give a lot of physical motivation for that. This is easy. So you take this wave function and k omega, you take this k, this omega, this f, and this g. Now, why choose such a k and omega? That they argue by Hilbert space. So they choose the k and omega to choose the psi, and from the psi they get the f and g. So is it clear? Like the commutator in principle would be calculated like the integration of something, like the commutator of x and pi. So for the integration, they use the k and omega like this from the mathematical point of view, and they use the completeness relation for this to correct. Okay, so this is one choice of F and G, which does get the job done. Okay, sorry. And this is for the DGS. They use something called variational method. They use the constraint like the inner product to be some constant and use the variation over that to find another set of K and omega. And as a consequence, another set of like the completeness relation to get this. Okay. Now the point is that this is a Fiasco and Poliner's paper, very good paper. They have shown that if you take this to F and G, what is the correction of the Casimir energy index? Remember, this is the normal Casimir energy. And this lambda 1 is for KMM model. And this is for DGS, which is good because now we can actually experimentally verify that which mathematically is consistent. So whether the variation method one or the maximally localized space one. So it actually gives a phenomenological difference between these two. Okay, so now we have played the same games. I'm not going to explain much later. So this rho we have taken, we calculated the shape function in the forms of this, where zeta is this. We calculate the BR for all this. So KMM with different lambdas, DGS with different lambdas, KMM with different alphas, DGS with different alphas. All of them satisfy the asymptotic flatness condition. And we have calculated the ADM mass. ADM mass I will probably explain for later because it is getting a lot of delay. The point is that mass in general relativity cannot be uniquely defined. The point is that it is inherently diffeomorphic. So one way, at least to bypass it, is that you take two asymptotic flat charge and you take what is the rough energy condition energies which is coming out of the normal. So just like you define the density as say d rho dt equals to grad of p, you can define the ADM mass like this. And if we calculate the ADM mass, I have actually calculated.
I think time is really.
Yeah. So I'll finish in 5 minutes, maybe.
Okay. Okay.
Yeah. So I'll calculate the ADM mass, and this shows this. Now remember, at B when it was M, we are getting exactly the Schwarzschild solution. So at least in ADM mass, we have gotten something that R by 2, the Schwarzschild limit when the lambda is 0 and the Casimir is present. FT gravity I'll probably tell later. The point is that the trace of T could be coupled into the field equation itself. Why? Because the cosmological constant, if it is natural, then it is actually given the Harkos idea that one can show that one can very well take the T as an arbitrary function for the sets of cosmological constant. Now it was done by the FRT gravity, as well as it has been shown that it is very consistent with the solar test. For FQT, the field equation is a little bigger. So this is the trace of this, because remember rho minus PR minus PT. And the Lagrangian is minus P. This is a standard exercise given in the Landau-Lifshitz as well as the Cordon-Owens one, that if you want the Euler equation, that is the U dot grad of P equals to minus rho, how should you get the Euler Lagrangian for the Lagrangian? And you can say that you can take the P as this. It's little complicated because you use the Lagrangian's multiplier as the continuity equation, etc. You can show that this is the theta we will get. I mean, after assuming this is the Lagrangian, and P is the total pressure. We have again taken the same metric, and for the FQT, this is the extra term. So as you see, the theta is the extra term rather than FQ. We have calculated the field equation with rho PR PT. And now the problem is that we have taken this time the non-linear one, and non-linear we cannot solve it. I mean, it's just the Mathematica gives up. So we have forced to chosen some well-motivated one, which is done in the literature, the phi and B, to give this. And we found the rho. And from this, because remember, this time we have chosen this. And we found the null energy condition. And we have now calculated what are the ranges of null energy condition which has been satisfied. This is the one it is done, and this is the plot of all the ranges where the null energy condition is satisfied, and it is the strong energy condition and the dominant energy condition also getting satisfied. Okay, now the junction condition I will probably skip that in GR, how to take the junction condition as the patch of 3 manifolds. And for the junction condition, this is so-called the extensive curvature. One can indeed show that the potential which would be felt by this, first of all, this is the expression, is given by this big expression. We have calculated the potential And it has shown that just like the Schwarzschild, there is a ISCO at the r equals to 3m. It has the similar properties. So hopefully in the event horizon telescope, etc., we can check this minimum and what is the potential, thin shell of the potential around the world we have actually calculated. So yeah, these are the rough idea, and these are the 3 papers we have done. This is the EPJC one, 2022. The second GUP one is in the general relativity and gravitation, and this is the Chinese physics C. Okay, in the next we will try to explain all these things which I've given to it, the Casimir effect, the FQ gravity, as well as the effect of GUP and the ADM mass. And lastly, I'll talk about the FQT, Israel junction condition, and maybe a little bit of this. Okay, so any questions, comments, suggestions? So
Yeah, thank you very much, Sayantan, for the nice introduction. Thank you very much. I don't see any questions. We had a few comments from Partha during your talk that probably help clarify a few issues. I don't see any questions in the chat or in the Q&A, but if participants want to ask a question, they're most than welcome to raise their virtual hand, and I can give them the right to talk. And in the meantime, I think Partha has a question or a comment. Partha, please.
Yes, Sayantan, I realized that. Can you go back your equation 44?
Here we go.
I think you should make it a full screen because this format.
Yeah, sure. So okay. So actually,
not healthy format.
Yeah. Okay.
Make it full screen as a press. Yes. Now equation 44.
Yeah.
No, it is not 44. Equation 44.
Yeah, this is 44, right? That
Scroll down.
Xij, Pij, right? Okay. So is there a lag?
Yeah, it's a phase lag.
Oh, okay. Maybe just.
Okay. Yes, now I can see. I can see.
Yeah. Okay.
Okay.
Yeah. Now
Suppose.
Yeah.
Now it's clear. Now, for your case, what is f of p square? Your case, what is an explicit form of f of p square and g of p square?
Yeah. So these two. So for the KMM, this is the 46, and for DGS, just a second. DGS, this 55.
Okay. But I realize that for the time being, if you choose, if you choose f of p square is just 1 and g of p square is just 1 by p square. Okay, because it is a general expression. You have a freedom
No,
to
that's
choose.
what the problem is, that it is not a general expression. The point is that if you want, I mean, again, that's what I guess the KMM and the DGS actually came. The point is that if you want the consistency with the so-called, I mean, the first one is the associativity, that is the Jacobi identity, as well as the Hilbert space, you cannot choose arbitrary F and G.
Okay, I mean, I am considering this kind of guideline. Yes. I think you can refer. I have already mentioned a paper and in your message link, so you can see the paper where they mention that this kind of algebra cannot satisfy the Jacobi identity, and how to satisfy Jacobi identity they propose something different way. So you should look at this paper.
In my WhatsApp or what? Where?
In the chat box. If you look at the chat box.
I can only see Professor Francisco's talk. Okay, maybe you can.
I can solve the mystery. Partha, you sent a message just to me.
Oh, I see. Okay.
Yeah. But maybe while Sayantan gives a look at the chat, if you send it again to it, we have Musav and Kozi who raised their hand and would like to ask a question. Musav and Kozi, please, you just have to unmute yourself.
Hello, can you hear me?
Yes, hi.
Nice presentation, but my question is maybe a little bit stupid, but I will ask it anyway. So I heard that you mentioned Schwarzschild in the first that there is no horizon, but I don't know, in my limited knowledge, Schwarzschild mentions a horizon, but you said the wormhole does not have a horizon. Can you
That's
please
absolutely
explain that?
correct. Yeah, sure. So, okay, so first of all, I will definitely explain in details in the next one, where I will actually construct this Morris-Thorne metric. But right now, let me just tell this. So this is what you are probably looking for. Okay, maybe we'll go to the present. So could you see the fourth point? No horizon can exist.
Yes, sir.
Yeah, exactly. So what does horizon means? That it is a infinite redshift, right? I mean, just like the 1 minus 2 GMM by R. I mean, okay, not the Cauchy horizon itself, but at least roughly the causal horizon means that 1 minus 2 GMM by R should not be equals to 0. I mean, at R equals to 2 GMM by R, the redshift is infinite, and that is a horizon. Why it is a horizon? Because somebody who is falling at the black hole up to the horizon, the time would take infinite amount of time in the Eddington-Finkelstein coordinate. So point is that in our metric, what I mean is that phi should be finite everywhere, in a sense that this, just a second. So did I write the metric? Yeah. So you can explicitly see that what phi should be. So in the Schwarzschild, what should be the phi? That is e to the power, that is phi should be ln of, maybe I should go a little bit here. I mean, okay, I know it's probably not the best, but again, like it's very difficult to, sure. So let me just erase that. So, okay, so as long as phi would be, say, ln of 1 minus 2 m by r, that would be correct for Schwarzschild, because e to the power log would be just 1 minus 2 mm by r. Now, what is the problem with this? At r, log is infinite. So this is a very good way of saying that as long as you write in the e to the power phi format, then phi is finite everywhere, ensures that your t never blows up. That means there is no redshift. So so-called I do not want a horizon mathematically boils down to phi r should be finite everywhere. Is it clear?
Yes, it is clear. Thank you.
Sure.
Thank you.
So yeah, that's a good question, because I would actually incorporate all those questions in the next class, when I will try to how should I say, like try to construct the Morris-Thorne wormhole by hand.
Excellent. Thank you, Sayantan. Thank you so much for a very nice introduction to the topic. I'm just worried now that we are ran a little bit over time.
Yeah.
And people might have other commitments that
Yes.
start.
Actually, I also have to go to home because the weather is a little bad.
I know.
Sorry.
We don't want you to get wet in the rain.
Yes.
So thank you very much. We will see you again next week. If you share the slides with us, we can upload them next to the announcement of your talk and the video on our website. Otherwise, the invitation to everybody to join again next week, and please share with your colleagues the interesting talk of today, so that maybe next time we have more participants.
So those who came a little late, this would be the rough agenda in the next. I will actually try to construction of the wormhole. I will talk about the Casimir effect and then the FQ gravity a little bit.
Excellent. Fantastic. Thank you very much. Thank you very much.
Also, thanks for giving this opportunity. I hope that it was not too disappointing.
No. It was very, very nice. Thank you very much. Thank you again also to Partha for facilitating your lectures.
Also,
and
thanks, because Partha actually gave me this opportunity, because we just know from the Facebook, but yeah, I mean, it's
okay, fantastic. And thank you to the participants for being with us. And I'm looking forward to see all of you again next week. Thank you. Thank you very much. Have a good afternoon or good evening, and stay safe. Yeah.
Bye.
Bye. Sir, can you close the meeting? I do